I think that we can begin the second session of our conference. And before we begin, I would like to thank the French Institute and the French Embassy in Israel for supporting the participation of architect Stanislas Chaillou in this conference. And I would like to invite Dr. JeanJacques Pierre, the Counselor for Culture, Education and Science in the Embassy of France, and the Director of the French Institute in Israel, to say some words, and really thank you so much for joining us here and for the support of your institution.
Merci Yael. Dear Dr. Yael Elat van Hessen, cher Stanislas Chaillou, dear Shany Barath, dear friends. It's for me a great pleasure for me to be with you today. And this online conference is the occasion, as the COVID-19 told us, to be able to organize ambitious online programs with talented professionals and researchers from all over the world. I'm really very impressed by the high quality of the keynotes and panels, and therefore I'm extremely pleased to introduce Stanislas Chaillou's keynote. As some of you might know, what we call CCI, Cultural and Creative Industries, are one of our missions for 2 years at the French Institute of Israel. Among many interesting topics, we chose to focus our new programs around design, architecture, and urbanism. And our innovation and technology are keys at implementing and developing those fields. Stanislas, you are an architect, but you are also a data scientist. So you are the best example of how high technology, and I know that you are working a lot in the field of AI, artificial intelligence, and culture, high tech and culture can work hand in hand together and help each other. Israel is a young, innovative country with an exceptional excellency in the field of new technology. And as for us in France, we have a long experience and traditional expertise in the fields of art, architecture and design. I hope very much that today's conference can be the start of a dialogue between our experts, our researchers, and our students from France and Israel on the theme of high technology and creative industries. I wish you all a fruitful keynote lecture, and I thank you for your attention.
Thanks so much. Thank you so much, Dr. Priyan. We really hope that it is the beginning of further collaborations, and yeah, we're really looking forward to Stanislas' lecture. And I would like to invite architect Shany Barath from the Technion to moderate this lecture. So thank you, Shany, and of course, thank you, Stanislas, for accepting our invitation and participate in this conference.
Great. So thank you, Yael, for the invitation to moderate this discussion, because I think this is going to be a really fascinating lecture. I would like to introduce Stanislas, and then the stage is completely yours for a chunk of time, and then we can have a brilliant discussion. So, a Paris native, Stanislas received his undergraduate degree in architecture at the Swiss Federal Institute of Technology in Lausanne, and his master's in architecture from the Harvard Graduate School of Design. Focusing his practice on architecture and artificial intelligence, he believes in the necessary integration of both disciplines to change our environment. Until recently, Stanislas worked as an architect and senior data scientist at SpaceMaker's R&D department, where he was in charge of developing AI research projects to assist and enhance architectural conception. And today, he's faculty at IAC in Barcelona. Stanislas has lectured extensively at Harvard, MIT Media Lab, the Sorbonne University, ETH, EPFL, and many more. and was awarded 2 American Architecture Prizes in 2017 and the Architectural Master Prize in 2018. He was also a recipient of the 2018 ZGF Scholarship for his past architectural work, is a Fulbright Scholar, an Arthur Sachs Fellow, and a Jean Gilliard Fellow at Harvard University. Quite a bio, I would say. So we're all intrigued to see your work, and I really look forward to the discussion that comes after that. So the stage is yours.
Thanks, Shany. Thanks so much for this introduction. Dr. Jacques Pierre, merci for all the kind words. And of course, Yael, and to all the conference, thank you for this kind invitation. I hope I'll be up to the task. I've got quite a few things to say, so I'm just going to jump right into it and not waste too much time. Can you please let me know if you can see my first slide full screen?
Yes.
Yes. Okay, that's great. So the topic of today, as explained before by all those introductions, is indeed AI and architecture, talking about their intersection, as it represents somehow a new approach for our discipline. As Shany said, I'm indeed an architect, but I've been training myself to also be a data scientist over the past years. And I've been trying to reconcile those two fields, those two disciplines that maybe were disconnected in the past, but are slowly starting to converge towards a new kind of practice that is integrating the two worlds for the benefit of the built environment. Just to shed more light about the path I took, but also to leave you with a takeaway about what is happening more broadly in the industry. As explained in the intro, I started at EPFL in a pretty traditional type of B-Arch, learning the traditional way how to make buildings as an architect. I later moved to Chaillou in Tokyo, where I started to work with what we call parametric procedures. I'll get back to the notion, but it was my first encounter at the time, as well it was for so many people in the industry, with the use of procedures and parametrics applied to design and to architectural design. Again, I will explain right after what we mean by parametrics. But again, for me, and again, for many people in the industry, this encounter happens. We train as architects, and then we encounter technology as a way to encode the things we want to create. Not too happy with certain shortcomings of parametrics. I later on moved to Harvard, where I went to study both, as said before, architecture and data science, and later on machine learning. And during that time, I went on the field within tech companies to really understand how certain companies were actually trying to implement those solutions within our industry. Those people were outsiders from our industry coming in. I've worked first with Flux, that later became Helix. Those companies were like the initial attempt from Google to enter our industry through this venture that spun out of Google X. It was a fascinating experience. I went back to school, did a thesis on the topic of AI and architecture, and then later on moved to SpaceMaker AI, where I worked until very recently in the R&D department. That path that you see here is nothing original today. It used to be maybe something a bit odd, I'd say 5 to 6 years ago. Today, it's something that is happening all across the field. We keep seeing people within our industry that are actually branching out, taking this tangent direction, merging the two fields to bring new solutions to a field. It's important to understand this because it really changes the tone of the discussions. We're not really talking about theoretical things and futures that might happen one day. We're rather embracing something that is actual, that people are actually committing their career to, and reminding ourselves of the actuality of those career paths, I think really changes the type of discussion we might have after the discussion. So stepping back from the intro side of everything, we could simply step back and just embrace for a second what is the role of the architect. There's countless definitions to this question, but of course, one harsh reality of the field is that even though we think of ourselves as free designers, more often than not, we are in fact in charge of mitigating, merging constraints that are in fact clashing together. The brief of a client, the context of a site, the regulations, certain qualities that surround our buildings. we're in fact in charge more often than not to realize the merging and the mitigation of all those things together. We would like to have a blank canvas and freely design. However, most of the time, all those competing vectors are the thing we have to wrestle with. In our ability to handle those clashing agendas and those mixed realities, we have to turn to our expertise. We train in school to acquire this expertise. We later on in our job acquire more of this expertise, and we grow as architects, learning those know-how. Within the expertise, I would argue that we can kind of see this as a two-layer thing, where there would be a fixed parts and somehow flexible parts. So to be clear, the flexible part is our own touch, our own way, our own style. What differentiates one architect from another, one office from another. There is a style that pertains to a given office that won't be seen in another. That's, let's say, the flexible part of our expertise, our own way to differentiate ourselves from the rest of the competition and also to express our own ideas. Within our expertise lies also the fixed part, which has more to do with a shared understanding of the discipline, a methodology, a systematic approach to how you make, build, achieve a given architectural design. You learn this methodology in school, then you perfect this methodology while on the job. This methodology that we've built together as a discipline and that kind of coalesce us all together as a discipline has in itself a history and is where technology has maybe a renewed relevance. I would argue that the flexible part, the part that is our own style, sometimes is foreign to technology. It can, of course, benefit from technology at moments where those two notions touches. But really, technology thrives when it comes to finding a common understanding, a methodology, building a baseline that we can all share. It's on those baseline, it's on this methodology that we craft together where really technology can enter our field and kind of provide actual value. Really understanding this really also sets the stage for the discussion later, because instead of thinking of too often as technology as this pervasive thing that kind of enters every single aspect of our practice, it's important to understand where it fits within our expertise, where it makes sense, and maybe where it fails to provide relevance. When it comes to our style, maybe it's less of a vector of change. When it comes to our methodology, the systems we want to build to help us create architectural shapes, then yes, it has indeed, or at least I think, a really acute relevance. This methodology, again, this way of to systematically think about architecture has a history. We're not the first one to tackle this. It has been ongoing since architecture has existed. Just looking back at the past 100 years allows us to understand where AI lands within our discipline. AI is, first of all, foreign to architecture. Even though architects in the past, in the 60s and 70s, have engaged with AI, it is something new, something foreign that is landing within our world and that some people choose to embrace. However, it lands in a field where systematics, where methodological approaches have already existed before. And it's important to understand how it relates, how it compares to those technological paradigms that have been in architecture already for a while. Just looking back at the past 100 years, we can distinguish at least 4 big movements, let's say. Modularity in the 30s, CAD, computational assisted design, in the 60s, parametricism in the 90s until today, and maybe AI as a new update, a new pass at structuring, consolidating this methodology that we can share in the discipline. It's really important to differentiate them and to understand that AI kind of comes as a relevant tool if and only if it complements and improves all the things we've seen in the past. If it is simply, for instance, something that resembles in every single aspect parametricism, for instance, and we'll get back to the notion of parametricism in a second. But if it's the same, why bother even in the first place investing time and resources into it? We really have to find really to distinguish the gap between what exists and what's to come. If we really we want to invest in those new technologies, it takes time, it takes resources. So let's be clear about what was before and what AI represents as a future for the discipline. So the easiest way to do that is to step back and just put our shoes in the most recent, let's say, big technological paradigm that has, that has shaped architecture. I'm very aware that in this conference, we don't have only architects. I'm sure there are some designers out there. That what I'm going to describe, parametricism, is something that has other names within other fields of design. However, it is a concept that I think any designer could relate to, because it is a structuring concept that, again, takes other names, but that I'm sure will resonate with things you've seen in your own respective fields. In architecture, parametricism simply amounts to this idea that design is a process that can be discretized. That's kind of the key statement, just to restate what parametricism was and still is for architecture. It simply means that if design can be dissected as a series of steps and decisions, maybe as an architect, I can formulate that procedure and pass it to a computer for it to be processed, so that later on in the design process, that computers can help me by going through those steps. So what you see on the slide here is like maybe the most complex slide I have today. It's simply a procedure that shows you how to lay out an HVAC system. So those big pipes that just run at the ceiling. How do you lay out the ceiling in the building? Well, there is a procedure to it. There's a set of what we call heuristics, rules, explicit rules, that we could come up with, right? We could just say, well, generally speaking, those rules shape the fact of laying out such a thing. In this diagram, we lay out a logic tree where we start at the start button, upper left here on the diagram, and we go down this logic tree, stepping from one step to the next. And from one step to the next, we have a decision to make, represented here by those arrows. So we turn essentially a typical design procedure into a logic tree, into a series of steps and decisions that, now that it's being formulated, could potentially be either transmitted to someone else, but again, in the context of computational design, it could be given to a computer. But parametricism is built around the word of parameters. And so understanding that parameters have an additional relevance here is really important. Design is an insanely complex problem. And there is a world of potential options that could be yielded for a given problem. Or in other words, for a given task, there's multiple answers, and especially true for many design tasks. What parametricism tried to do, and it's trying today to do, is to hook parameters to every single decisions, so that as you change the parameters, as you change the values, what you yield towards the end is something different from another set of parameters. If I change the parameters, I get different answers towards the end of what we call a script, or these procedures here. Those parameters are essentially a way to express the idea that there is variability in the design process. Therefore, there should be a mathematical way to account for the variability of potential design options. Here is parametricism simply summed up. It's a way to think of design as a procedure so that we can discretize the design process into a procedure. This procedure has values, parameters. As we change them, we change the outcome. It has created amazingly great solutions. Parametricism still today provides countless solutions to us architects. However, it kind of falls short to answering two essential questions. The first one is my procedure, you see here, holistic? And the second one is my procedure is relevant? So let me explain. Is my procedure holistic? So as you pick and choose certain steps and certain decisions, and as you unfold the procedure that is supposed to describe the thing you try to do, you're in fact essentially narrowing the scope of potential things that the script can generate. Knowing if for the task you're trying to achieve, you've narrowed the scope the right way is an incredibly hard task. By proceeding in such a way, by explicitly encoding everything and putting in place those decisions and those steps, it's in fact really hard to know whether you've scoped the problem the right way. So in other words, for the task you're trying to tackle, have you scoped the procedures in the right way? Knowing this is in fact really hard, and one of the key shortcomings of parametricism. Another one is my procedures relevant? This has to do with the notion of parameters. As soon as you've set up these procedures and you have parameters in place, the idea is to change those parameters to move in what we call in mathematics the problem space. It simply means the realm, the spectrum of potential options. Knowing in this problem space, in this space, where the best potential area is, in other words, where the best designs should be found, is a really hard task. And because design is an immensely hard endeavor, knowing the right balance of parameters is often close to impossible. For simple tasks it is, for complex tasks it gets really hard. Often we turn to the computers and offer those parameters to computers for them to balance out. That is what we call optimization, for instance. Optimization simply meant, well, if the task is too complex, I can simply hand over the parameters to a machine. And given a certain grading system, the machine would tweak the parameters to land in the problem space in a better spot, in a place where hopefully options are more relevant or more pertinent to the thing I'm trying to create. Again, machines sometimes could do this, but if the design space is too complex, if the problem you're trying to emulate is too hard, well, in fact, you would end with suboptimal answers. Simply said, you won't get the best out of the problem space. So those two questions of holistic and relevance really shows where, unfortunately, sometimes such explicit procedures can fall short of offering meaningful answer to architecture. This is why, in fact, AI can really step in and bring an alternate way to see the problem, to hopefully bring new answers and new solutions. So there's many types of AI. The one I'm working with could be also called statistical learning. So we'll explain the two terms, but again, to be clear, there's many types of AI. The one we're going to be focusing on is the one I'm most familiar with. And again, it's called statistical learning. So let's be clear, statistical and learning, let's start with statistics. So given a phenomenon that you're trying to emulate, mimic, the question is, what is the right tool set to, by the end, paint the best representation of it? When it comes to finding the right mathematical tool set to do it, parametrism said, well, I'm just going to look at the phenomenon and descriptively, explicitly draw the rules that should explain the phenomenon. Statistics works actually completely in reverse. I would take the same phenomenon, but instead of trying to explicitly coin down the rules, I would rather try to observe again and again thousands, millions of occurrences of the same phenomenon, while trying, thanks to the machine, to pin down the commonalities, the common characteristics across observation and samples. So we're shifting from the rule to the characteristic. We're shifting from description to observation. We understand it's a different approach, but we'll see next where, in fact, it opens doors to new approaches, to a new way to think about modeling architecture. So this is for statistics. But again, as we said, statistical learning requires us to understand, well, where learning, the notion of learning falls. So to do so, let's turn to our discipline architecture and to a tangible, concrete example. So in this image, we see what we call a training sequence. So essentially, a training sequence is something that expresses the notion of learning. With parametrism, when you had encoded a procedure, when you had laid down this kind of tree, it could right away be used by a machine. The code is a procedure, the machine processes the procedure and just go down the rules. When it comes to statistical learning, however, the idea for a computer is to look again and again and again at examples, at samples of the data. That in turn allows the model to further refine its weights, or in other words, just to refine its intuition. It's not the right word because, of course, let's say it's just a metaphor. But again, to refine its model to better mimic the phenomenon by the end. So that time it takes for the machine to really tune and refine its ability to mimic the phenomenon is called the learning process. What's happening here is that I'm having the model learn how to draw an apartment floor plan. The colors encode the program, and the black poché is the thickness of the walls. What's happening is that gradually the machine is refining its ability to represent a floor plan. It starts from mediocre image in the upper left corner here in the slide and ends up with roughly okay floor plans that aren't perfect at all, but that are an initial pass, let's say. So all those images constitute the training sequence from previous slide. If we just look at 4 samples picked along the way, maybe we'll convince ourselves that this is in fact meaningful for us. So at the initial stage of learning, the model only gets the notion of footprint. It roughly creates a black patch that has no understanding or no features or no architectural features, but it has the idea that, well, an apartment should have some kind of a footprint. After a few hours of learning, suddenly it starts having this kind of poché line around, which is essentially a facade, and the colors are being infilled as the program is being grasped somehow by the model. Of course, the ratio of the rooms, the adjacencies, the notion of enclosure, everything is off, but it's a beginning. Moving on to later images, further along the learning process, we'll start to see certain features that we're more accustomed to as architects. Notion of columns, so enclosures in between rooms. Adjacencies are starting to arise in between the rooms, meaning the kitchen is closer to the living room. The living room is kind of a hinge between bedrooms, but it's not perfect. Things are really still way off. If we step all the way at the end, what I'm not going to say is that it's a perfect floor plan, that should be taken as architecture. It's simply an initial pass, a first try, a first attempt to provide an answer to a given problem. But again, it needs to be lifted from a solution to creation. Architects have to embrace this and refine it, nurture it, change it, edit it, so that it would actually make sense within the context of the architecture. But it can provide some amount of resolution. The adjacencies are okay. There is some amount of enclosure around the rooms. There is indeed openings on the facade. It's somehow kind of sound. Again, it's not perfect. It's just an initial pass, a way to maybe go faster at the beginning of any design process. Now that we have those two notions put in place, statistical learning, and we've seen how it kind of lends in architecture with a tangible example, I just want to go quite quickly through the tangible contribution that AI brings to us architects when we design. AI can contribute to other scales of design, can contribute to other moments of our industry, to the construction phase, to the operation phase. But when it comes to conception, to design, and to us as architects, I think three things really stand out. The notion of flexibility, of options, and analysis. Let me just explain. So for flexibility, the idea is that more often than not, we are kind of trying to do two things at the same time, solving and playing. We want to solve certain problems, certain constraints, while being able to play and explore potential options, potential solutions that do not have, that does not really only addresses the notion of performance, that are trying to be relevant given our client, given the place we're building in, the culture we're in. This kind of tension between solving and playing is sometimes what makes the design process very unflexible. We might want like an amazing amount of flexibility and freedom, and however, the constraints are pressuring design and putting us in a terrible place. What's happening here is that once I had trained a given AI model, I could create this interface where on the left, one could input constraints. In black, the footprint of an apartment, in red, the position of the windows, and in green, a tiny square for the entrance door. Once this was done, the architect could click on transfer, and then the left side input would be transferred into the right side output. What happens, what you see literally in the animation, is that iteratively, with actually quite a lot of flexibility and freedom, the architect can play with the outer form of the apartment while the internal layout is being partially solved. It can be better, can be improved, but there's an initial resolution that can happen that allows the architect to have this, at a given scale, a certain amount of flexibility. That idea can be brought to other scales, to other moments in the design process. It's true to architecture, but again, as there's a lot of designers today, I think this can be thought as something broader than just the architectural field. There's moments in any design process, and those moments can again be moments of tension between solving and playing. What I've been trying to do in this work is to isolate certain moments along the design process of an apartment building, model 1, 2, and 3 here on the slide. And for those moments, each pair shows input and output image. So the first model would go from an empty site to a full site, meaning has generated a footprint of a building. The second model goes from an empty apartment to a filled apartment with rooms. The last one goes from the program of the rooms, encoded by colors, to the furnishing of the space. In between, instead of making a one-stop shop, one big model that would automate everything, what I would rather do, what has been happening here, I've chopped the design process into those tiny steps so that the designer is actually always there to do the big trade-offs, to make the big decisions. He or she is able to step in between the models and make those decisions that do the 20-80, the 20% of the cost and make 80% of the effect. It's really important and something that I think AI can do quite amazingly. You can encapsulate moments of the design process and really release the freedom in between, so that those moments in between are actually moments of playing rather than pure moments of solving. But for results that I think are even more exciting, it's important to understand that we're not trying to play just freely like that. The point is to play while handling constraints that are meaningful to us architects. So here's typically one set of results where footprint on the left takes into account the footprint of the apartment and the openings, and you get results on the right. So here, what is relevant to architecture is, well, the influence of openings and their respective influence on the layout of the plan. We know that as you change the openings, things are going to change into the plan. Another example, and those results are really exciting, is this idea that often program is conceived through the lens of a mix of room and an element in space on top of it, meaning I want those types of rooms, and I want that room to be there specifically in space. It's just showing you a typical way to think about architecture for a given step. Laying out rooms in space, sometimes you might want to have an apartment type of program while having a spatial feature on top of it. You want the bedrooms to be there and there. So the green patch in the left side inputs here are in fact the position of the bedrooms. And as you see on the outputs, the bedrooms are indeed in the right position while the rest of the program is being handled and resolved by the model. A last example, but is also quite, I think, quite telling, is the fact that more often than not, the structure is a key constraint on the floor planning of an apartment. Load-bearing walls go through the space, and you have to handle those realities. They actually pressure your design as you need to mitigate their impact on the floor plan. By encoding those walls with those green dashes in the left side input, we are able to handle those constraints and have meaningful answers on the right. Again, those are just initial passes. Later on, an architect has to go back at this and just play with it and improve it, of course. But it's interesting to see how those key constraints that really put the pressure on so many things we do can be embedded in the very question we ask to the computer. Of course, I'm not the only one to work on this. There's countless researchers doing amazing work. This is typically a project that I admire very much, done by Danev and Müller. They are the professors and lead scientists at the Digital Structures Lab at MIT. This brings us to a completely different space, which is the one of structural design, where constraints are all over the place. The question for structural design is how much can we explore new shapes while keeping in check the performance? Well, again, solving and playing. The problem is that for structural design, very often, those things are completely clashing. And in fact, the flexibility is close to none. What Danev and Müller have done is worked on a model that actually can isolate the performance on one hand, while later on allowing designers to explore different shapes while keeping the performance in check. So again, this pertains to this idea of flexibility in the design process, but this time applied to structural design. Another quite amazing project from Kyle Steinfeld at UC Berkeley. So in this case, Kyle has been working on the idea of very early stage atmospheres and for the design process. If you have, as an architect, a simple white plane and you're placing massing, you're essentially doing those early step of the design process. You might want very early on to know how the atmosphere could look like. How is this massing actually creating a certain life in the streets? Well, what Kyle has done is train models for given neighborhoods, where as an input, you could then give to the AI model just simple massing on a white plate, and the whole thing would be textured according to a given neighborhood style acquired by Kyle's model. This also pertains to the idea of flexibility, because you can really quick change the massing and see what potentially the atmosphere could be in there. This is very speculative, I'm very aware of that, but at the same time, it touches more upon the poetic aspect of architecture. Not everything is about structures for planning and performance. Some aspects are more about the sensible part of architecture. A last example that I put in there just because it's a good reference to have, because it's been all over, is Holon alumni. I've been working at UC Berkeley on this model that is translating a simple layout of the bare bone structuring element of a facade into a rendered facade. That model is immensely well known and has done great things and is starting to do great things for architects as they are able to reshuffle the layout of structural elements for a facade to later or a second after see how the facade could potentially look like. So here are examples where in the design process, we can bring hopefully flexibility thanks to those AI models. Another question, another contribution of AI is the idea of option and optioneering. So in clear words, the idea here is to translate something that predates AI, that is the need of options for the design process. In many architectural offices, playing with foam models very early on in the design process is a thing. You have armies of people crafting foam models to create arrays of options that allows the design process to be this pick and choose thing where you open the funnel, collect options, choose a certain one, and then do a new funnel. That's a way to design. And that simply stresses out the fact that, yes, options do contribute to the design process. AI can say something to that. Behind the notion of multimodality is, that is kind of a technical term, is hidden the idea that one input can yield multiple output. As you see here on the slide, the input on the left creates 4 potential options here on the right. They are not completely different, but they still allow some kind of choosing within a space, a design space. But what is new, what is refreshing actually with AI is that a notion has arisen within the scientific community to handle this notion of multimodality in a more structured, meaningful way. And that is the notion of a latent space. So I'd love for everyone to go back home today with this notion of latent space clearly coined down in their mind. I'll be as concise as I can be. The idea behind the latent space is that an AI model, if trained properly, could potentially create a map, a structured map of the phenomenon you're trying to model. So to be clear, let's take an example that will simplify the idea. If we train an AI model to generate circles and squares, if it's trained properly, it's going to create this, and if it has the right architecture, it's going to create this latent space. That is an n-dimensional space, meaning a space with multiple dimensions. In the space, the model is going to disentangle, dissociate the things you want it to learn. So if you wanted it to create circles and squares in a spot, in a given area of the latent space, will be the circle notion. On the other hand, will be the square notion. What you can do essentially once the latent space is structured and the model is properly trained, is to choose a point in latent space and move in this latent space to create output values for your model. So if it was trained for circles and squares, if you pick a point right at the center of the circle area, the output would resemble output number 1 here on the slide, the perfect circle. If you then, another example, pick a point in the square area, well, you will yield number 5 here, a perfect square. So we're not really interested in 1 and 5. We know what a circle is, what a square is. What is much more interesting, especially when it comes to architecture and formal experimentation, is the in-between realities, the in-between categories, 2, 3, and 4 here on the slide. So let's be very clear. With parametricism, to get an equation that would get us from 1 to 5, we would have had to explicitly encode a procedure that isolates given parameters and creates rules so that as you change the parameters, you go from 1 to 5. With a latent space, we have not encoded this. The latent space has handled this learning of features for us and has been able to model, hopefully, how you would go from 1 to 5. So much so that as you move in latent space from circle to square, you create in the output option 2, 3, and 4. Going from square to circle is a very simple thing, but it only stresses out 2 things that are essential to understand the latent space, is that it can handle both explicit and implicit parameters. that could be mapped onto distinct, disentangled dimensions in the parameter space, so that you can move in the space knowing which feature is being emphasized or decreased. With parametrism, let's remember, we were only modeling explicit things. We were only modeling those things that we could explicitly name. With a latent space, the explicit can be captured, but the implicit, those things that were too hard to actually formulate, could potentially be grabbed and mapped onto a given dimension. A second property of the latent space that is fascinating is its consistency. In clear, it's a space where things that look alike are close to one another. So when you move in latent space, two neighbors are almost of the same spec. That means that it's very reliable as a tool once it's trained to use, because as you move, you go along a gradient. You move along a slowly, let's say a gradient of slow differentiation. This is where all those images that you've seen on the internet, where you see those faces melt and change, comes from. You move in latent space and the value gradually changes. It's predictable as a behavior, therefore usable as a tool. It's interesting to architecture. For circles and squares, it was of course irrelevant. It was some simple examples to explain the concept. Those images are very muddy. They aren't quite precise. Training those models can be a bit tricky. However, those results you see here are simply showing you that once it's trained, and for canonical floor plans of apartments, you can then move in the latent space and have a solution here in the center of the circle being a weighted result of the influence of given typologies of given things in the latent space. The circle and the square are here typology 1, 2, 3, and 4. The same idea can be mapped in a more scientific, rigorous way. And in between, you could literally explore in between categories, sitting between known quantities, typology 1, 2, 3, and 4 here. As a design tool, it's extremely powerful and very relevant to help us get this idea of holistic. We can map literally the realm of potential option. We can saturate, almost of course, not quite, saturate the design space in a very useful way for us architects. But again, other architects are working with this. Here's Daneve Muller playing with this array of options that all stem from a latent space trained to have performance structural options. Same thing for Stanford's work, where you have all those perspectives stemming from a latent space through which you can move to generate different types of neighborhood. The last topic in one slide is analysis. Essentially, the idea is that, and I'll go real quick because I know we are a bit short on time. The idea behind the notion of analysis is to say, well, we used to work with simulation in our industry, but in fact, maybe less so than in other industry. Simulations using physics engine are costly and takes time to parameterize. Using AI models, we have this ability to map input to output and to hopefully do predictions of certain simulations. Predictions aren't at all as, let's say, accurate as traditional simulations, or at least for many phenomena. Taking here on the right, what you see, the images you see, the pair, those are two images stemming from work done at SpaceMaker, where you see the footprint of buildings in the neighborhood, and we're computing the gradients of the diffusion of the noise in this neighborhood. That is a very expensive type of simulation to run, and to do it, let's say, the traditional way with a physics engine, we would yield the image on the left, the one that takes 10 minutes to parameterize and then to run. It's expensive, it takes time. The one on the right is a less accurate prediction of the simulation using an AI model. That runs in 0.05 seconds, so the contribution is obvious, and allows you to do this thing here on the left, which is live analysis. As you play with the massing, as you play with an architecture, you can have, as a live feedback, an idea of the performance, which is crucial to us architects, knowing how the things might perform. Here's for another aspect, the idea of analysis. I see the time, and I think for the sake of having a discussion after it, I think I should skip through the last slide, unfortunately. So I won't be discussing the 3 last slides. We'll just go real quick towards the end of the presentation. It's not too important. I think the most important things have been said, and I'm happy now to open the floor to questions, and Shany, I'm very happy to have an exchange on this.
Yes, so first of all, thank you for this really fascinating talk. I'm sure many of us have seen your work. So there are also some questions that came from the audience, which I will relate to. But I would like to put forward 2 topics maybe, and also to bring in the topics of the audience into these themes. The first one relates, I would say, to the first trajectory would be the input. So at the end, when we're discussing training, AI, which is based on training, we also need to understand the quality of the data that we're inserting for the training itself. And one of the questions that is coming from the audience is, if the data is conducted on knowledge that already exists, on data sets that exist, what is the potential to create new ideas? And I think you related to that a bit when you were starting to talk about predictions, but I think it would be very interesting to highlight that a bit more in relation to the question that is coming from the audience. Another thing was that came up, I will just read it quickly, is that the answer cannot come from old buildings, which didn't answer relevant questions of today. For example, your training data seems to be based on Western European classical floor plans.
Very true.
That might not represent the whole solution.
Yep.
So I think this is a really important point coming from the audience. Yep. And the second thing that I would like to discuss is the idea of the design tool and the inclusivity of the design process. So are we creating tools today for the professional, or is it enabling us to bring the public to participate in the design process? And I'll just give one example. Today, taking the floor plan, many times we see as architects, people coming with their idea of how the floor plan should be designed. I want my living room here, my sleeping room here. And is this a way, or intuitive way, a structured way to bring the public into design processes? And what does that mean about decision-making processes for the architects? And what does it mean about the architect's role in these new workflows? So I'll start with these two, and we'll see how much time we have, and we can roll on from that.
Of course. Okay, thanks so much. No, those are very, very relevant questions. So I'll go straight to the point. So the first question is, if I remember well, how do we create? Sorry, could you ask again, just to be sure I'm right on point?
No, the question was about, on the one hand, the quality of the data that we of the data sets, but also how do we create new ideas, new information if we're using existing data sets?
Yes. So the first question then about quality, one very hard thing for us right now, and it's starting to be easier, is data scarcity. So we end up with actually poor quality data because there is very few. Recently, things have started to be more structured. So there are more databases out there of like academic data sets that are making things easier. But it's true, I absolutely agree that the quality of the data absolutely conditions the quality of what might get out of it. That's also where, as architects, if we properly train to those techniques, we might be able to do great things, because in fact, we're not the only industry where data quality is a challenge. There are other industries really wrestling with the same problem. They have come up with ways, and there is a lot to be learned from other industries in this respect. So, and this is personally what I've experienced working with people, for example, in the automotive industries. There were friends that were absolutely insightful when it came to helping me think about the data and the quality. So this is really, I think, for those questions, really where we should look to our neighbors and how they handle these kind of topics. The next question is even more, I think it's great because it's really something that is a topic. How can you do good things if you only look at the past, in fact? That really is a question. So something that predates AI, it's just our own way to create. There is many types of creativity and ways to go about being a creative agent person. But one task that we perform as designers is the idea of transposition. We take instances, we observe certain instances of reality, and with a new or changed context, we think about the principles we observed to transpose them to a new context. It is indeed something we do. It's not the only thing we do. It's a thing we do. And it's part of a tool set, of a set of tools as architects. I think what is really powerful with AI, and it's maybe one of the things it can do for us, is be kind of rigorous and precise about those moments where we apply transpositions, for instance. So not everything is bad from the past, but indeed some things aren't too great. What is amazing here is that we have a shot at actually studying the past, filtering it for things we don't want to reproduce, while having a rigorous way to transpose what we thought was great to new contexts. It brings us back to the topic what was discussed before, the idea of bias. Bias predates the arrival of AI. We have bias as humans, of course. But what is great here is that we have a shot of having a tool that helps us study this bias to actually filter out what should be removed and keep what maybe is meaningful for new context. Another way to look at this problem is that, or maybe a more experimental way to look at this is that bias can also be in our discipline, things such as style, for instance. And in fact, there is functional reasons to have given styles in given context. Studying the function of style is an ongoing research topic. It has been around for a long, long time. What is fascinating is that we have this ability to apply AI, to studying the function of style. So you see, maybe it's a more positive outlook on the notion of bias, meaning certain things in architecture are positive things like a given style, and that can be thoroughly studied through the application of AI systems to it, which I think it's an avenue of research that is indeed fascinating. Inclusivity then. So inclusivity, yes, I think that's a very relevant one too. Maybe I don't think it's solved. I don't think AI solves something here. It's just a new thing in our tool set. But what it can do for us, and this goes back, for instance, to the analysis part of the discussion. It helps us do informed decisions, and it democratizes certainly our ability to forecast the performance of given designs. That is great often in the back and forth we can have with the greater public, because as architects we do have an expertise. We do have something to bring to the table. Removing entirely the architect from the process in this exchange with the public, at least it's not a path I strongly believe in. I'd much rather keep an architect in the process because I think they have tangible expertise to bring to the table, but they can absolutely now rely on way faster feedback loop for certain aspects of the thing they built. The performance is one, and we saw an example. There are things where it's going to take a long, long time, and we could even argue that it would be hard for AI models to go there, where the architect remains absolutely crucial. The relevance of an architecture to sociological context, to a demographical context, to a given cultural context, is something that is so minute and complex to grasp that it requires, I think, an architect, and it's still today something that shapes and structures the expertise of an architect. This is not something that those AI model really could help us bypass. So to be clear, on matters of performance, yes, absolutely, it brings a way more transparent and iterative feedback loop between us and the public. How is going to be the daylight in a given neighborhood, for instance? It's a topic we could study in real time. But when it comes to cultural significance, to sociological fit, that is something that is part of the agency of the architect, where AI models will have a really hard time entering, I think.
Perfect. Another question, I think ties back maybe also to the session that we had before. I think we have 5 more minutes, yeah, right?
Actually, we have to wrap up and go on to the next panel, although it was fascinating, and I think that we could have continued a much longer discussion.
No problem.
So thank you, Stanislas, and I will find the opportunity to ask you one last question.
Yes. We thanks, Shany, and thanks, Yael, for this kind of invitation.
Yes, thanks so much. It was really, really fascinating. So thanks both of you. And I would also like to thank Laura Schwartz from the French Embassy for facilitating this talk. So thanks a lot.